Patrick. In this video, my teammate Avril and I will be giving you an overview about the project that we did for our data analytics course in PES University. The goal of this project was to study and compare various classification techniques and algorithms to classify epileptic seizures in order to aid its better diagnosis in the future. So what are these epileptic seizures? Seizures are brief episodes due to abnormal synchronous activity in the brain. Their outward effects may involve momentary loss of awareness and the jerking motion of the body. And these recurrent seizures are characterized. And our study will be using two data sets. The original data set comes from the paper that is indications of nonlinear deterministic and finite dimension structures in time series of brain electrical activity by Foreman et al. They have classified seizures into 5 categories, that is the Z, O, N, F and S class. The Z and O are termed as normal, N and F are seizure free, and S is the seizure class. So what we'll be doing in this project is classifying it into one versus all, that is S class as one and the other Z, O and F classes as the other. The other data set that we'll be using is from the UCI ML repository. It's basically a 1-second random sampling of the original dataset. In the models that I coded up, I use frequencies as features. In order to obtain these frequencies from the time series data, I used a Fourier transformation. What a Fourier transformation does is it converts signals from the time domain to the frequency domain. After obtaining these features, I pushed them to 4 different classification models, that is KNN, K nearest neighbors, SVM, random forest, and a feed-forward neural network with 3-layer architecture, 1 input layer, 1 hidden layer, and 1 output layer with fine-tuned neurons and other parameters. On repeated training, testing, and statistical analysis of these models, I found that KNN with 3 nearest neighbors and random forest algorithm perform way better than SVM and a simple feed-forward neural network. On checking the confusion matrices of these models, I found that SVM could learn only one of the classes properly and it misclassified the other classes. So Avril will be talking about using time series data by itself for classification using convolution neural networks and recurrent neural networks.
Hi, my name is Avirul, and in this part of the video, I'll be talking about the recognition of epileptic seizures in time domain. In time domain classification, we take the signals outputted by the EEG and feed them directly into our machine learning algorithms as input features. But before we move on to the task of classification, we must take a look at our data first. On plotting the data at first glance, we find it hard to notice much of a difference between the signals corresponding to seizure activities when compared to the ones that don't. But on further inspection, we notice that the signals representing EEG seizure activity have a slightly larger wavelength. Now moving on to the task of classification, we first train our machine learning model to recognize what an epileptic seizure signal looks like. We do so by feeding it lots of data consisting of signals and labels. Each label represents whether the signal corresponds to epileptic seizure activity or not. Now we move on to the testing phase. In this phase, we compare various machine learning models based on the accuracies with which they are able to predict or classify epileptic seizures. Based on the scores obtained by machine learning algorithms on testing data, we can say that out of all the machine learning algorithms tested, recurrent neural networks are best suited for the task of classification of epileptic seizure signals, followed by the KNN classifier. However, before coming to a final conclusion, we must also take a look at the confusion matrices of recurrent neural networks and K-nearest classifier. On analyzing the KNN classifier's confusion matrix, we see that the KNN classifier, if used, produces very little false positives. But on the flip side, the KNN classifier does not recognize half the epileptic seizures in the testing data, leading to a lot of false negatives. The confusion matrix of the RNN classifier has very few false negatives, but the RNN classifier produces more false positives when compared to the KNN classifier. To put it simply, if we were to use the RNN classifier over the KNN classifier for the task of epileptic seizure detection, we would observe a few more false alarms, but the degree to which we could recognize epileptic seizures would increase drastically. To conclude the discussion about the classification of epileptic seizures in time domain and frequency domain, it is worth noting that almost all the machine learning algorithms performed a better job of classification when classifying epileptic seizures in the frequency domain. However, RNN in the time domain outperformed every other machine learning model. Thank you.